is a three-phased system where the supply is a balanced source, whereas the demand, the load, is an unbalanced source. So it's a three-phase, four-wire system. That means three wires are there for phase A, phase B, and phase C, whereas the fourth wire is a written, that is a neutral wire. So three-phase, four-wire system, it's normally called, and it is unbalanced because look at the A phase purely resistive load, B phase has resistance but minus J3. This is a capacitance load is there, so it's a capacitive load, whereas the C phase is the inductive load. So three different values of load impedances are there in three different phases. So therefore, even if the supply is balanced, as you can see here, 80, 80, 80, the magnitudes are equal and the phase angle is 0 here, minus 120 and minus 240. So this source is a balanced source of voltages. So VAN, VBN and VCN are the voltages here. The currents IA, IB and IC will be unbalanced currents, and this neutral will be taking the current whatever is the unbalanced to this point. Now if you consider this neutral point as the ground point, the 0 volts, so then we have the voltages of all other lines measured with reference to this. So this, if you consider as a ground, so this also automatically becomes a ground because it's connected here. We are not assuming any resistance or impedance for this lines itself, but this is about the case. Okay, let's come to the question actually. So what is the question? Question is calculate currents in all branches and complex power in each phase for the following system with three-phase balanced supply and unbalanced load. So it's pretty straightforward question. So you may pause the video now, try the answer yourself, and later you can compare your answers with my answers. So let's try to solve it myself. Now, if you look at it, it's in a way it's quite straightforward because here the neutral wire is there. So this voltage AN directly applies across the impedance ZA. So therefore, the IA current will, I can directly write here, IA will be nothing but VA divided by ZA. So this is VAN divided by ZA. So VAN is the voltage of A with reference to the N, which is a neutral point which is grounded. So of course IN will be different. So we'll find what is the actual value of IN through KCL. But first, the IA can be easily determined like this. Similarly, the same logic. So this is a ground point, and VB is the voltage here, and then ZB is the impedance, and then it's closed here. So IB by that logic will be VBN by ZBN. So we all know that these are alternating quantities, AC voltages and AC impedances and everything. So these are all complex numbers. So each of these numbers will have real and imaginary components. So similarly, the IA, IB will also be complex numbers. So all the time when you're working in AC circuits, you need to keep that in mind that you are working with complex numbers. So therefore, I can actually omit this symbols here. So it is understood that these are all complex numbers. So similarly, IC. So this voltage is, you just have to look at this entire part of the circuit actually. So this voltage is directly applied to this phase, and then return is like this. So therefore, I can write VCN by ZC. So like this, I have a simple calculation, find all the currents. You can represent this in the form of a matrix. So that is IA, IB and IC. So the three currents, if I represent as a vector, so then it's nothing but the voltage vector VAN, VBN and VCN. And this I have to divide. So this is like I'm using a dot slash notation, that is division, element wise division, or okay, for the time being, let me just use like this ZA, ZB and ZC. Okay, so I would like to do this calculation. So for this calculation, I'll do it using. You can use a calculator, scientific calculator, to do this, but I'll be using a octave interface, which is nothing but similar to the MATLAB. It has a syntax, and we can run this commands like this. So in the middle, as you already see in my other videos, so this is the place where I write the script, and on the right hand side will be the solution. So let me define the voltages to begin with. So VAN. I'll simply write VA in this just to have a short notation. So 80, and here the imaginary component is not there, so I'll keep it 0. Then VB. Now, how to define the, if I go back to my video here, this voltage VBN is 80, 120. So let me again just give it a recap. If you had seen my other videos, this is just redundant, but I'll just explain. So this 80 is the magnitude and 120 degrees negative is the phase angle. So this, if you want to represent it as a complex number, you will write it as 80 e to the power of minus I into 120 into theta, that is 120 degrees. But to convert the degrees into radians, I have to divide by 180 degrees and multiply by pi. So this factor, I have to pi radians. This is just conversion of angle into radians. So of course this minus actually should go inside, so minus 120. But anyway, this is the notation. So let's, if you do this notation and if you execute this, then you will get actually the real and imaginary component. So, or mathematically speaking, it is just 80 cos of, I'm sorry, sine, no, cos. The real component will be cos, and then plus j 80 sine of 120 degrees. But all these things, anyway, we are going back. I think all of you are aware, I'm assuming, about how to handle the complex numbers and how to handle AC quantities. So let's define this in our octave interface. So 80, and here the syntax is exp, that is exponent, and here I have to take I multiplied by minus 120 divided by 180 degrees multiplied by pi. Now, if you notice, this is a code. I am directly using the symbol I. So by default, if I just use symbol I without defining it, automatically the MATLAB will consider it as the imaginary symbol for imaginary component. The value of I will be square root of minus 1, if you already know. And pi is the pi, that is just the constant. Now VC the C phase voltage, that is again 80 multiplied by exp. So here I multiplied by minus 240 divided by 180 and multiplied by pi, just for conversion to radians. Now I have defined the values. So similarly, A phase impedance, B phase impedance and C phase impedance I want to define. So what is A phase impedance? So I remember it was 5 ohms just, and let me refer to B phase impedance, 2 minus J3. So here I'll use 2 minus 3i. So whereas ZC, so J we use in electrical notation, whereas in mathematical notation we use the I, and that's the only difference. And I should follow the number, whereas here in electrical representation, J will be before the number. That's the difference. Again, I am assuming you know how to handle this numbers. So 4 plus J3 is the ZC. So 4 plus 3i I will write here. Now I have defined everything, so I can write IA is equal to VA divided by ZA. As simple as that. So I can just copy this and just change the names. Instead of IA, I'll find IB. Instead of IB and IC. So this is C, this is B, and here this is B and this is C. So let me save this program and then run this. So on the right here, you can see the results. So VA is 80 volts as expected, and VB is minus 40 and minus 69.282. So this is the B phase voltage expressed in the form of complex number, and VC is also like this. This is minus 40 plus 69. Now I have impedances 5, 2 minus J3 and 4 plus J3, and the currents are as like this: 18, 9.8, minus 19, and so on. So now if you look at the currents, these currents are expressed in rectangular format or complex form. Now I want to know what is the magnitude of the currents. So IA magnitude, of course, it is 16 at 0 degrees, but IB, I want to know what is the magnitude and what is the phase angle of IB. So to get magnitude and phase angle, I'll just form a small matrix like this, two elements. First I'll take the ABS of IB. So this is just, this first element in that matrix just calculates the absolute value of IB. And next, angle of IB. So this will give me the angle and absolute value. However, this angle will be in radians. So I just multiply by pi and divide, I just multiply by 180 and divide by pi to uh, to convert the angle back into degrees. So if you notice above, it is divide by 180 and multiply by pi, whereas here it is multiply by 180 and divide by pi. It's just the opposite conversion, just converting radians to degrees and degrees to radians. Similarly, I'll do it for IC. I can even do it for IA. Let's do that. Although we already know the result for IA, because the load is purely resistive, the imaginary component will not be there here. So I hope everything is correct. So again, I save and then execute this program. So here I'm getting 16, 0, 22. This is the absolute value of the magnitude and this is the angle. So let me note down these results. So I have, after this calculation, so I have IA is 16 at 0 degrees, then IB is 22.19. I'll write it. It is 188. I just rounded off, and the angle is minus 63.69 or minus 63.7 degrees. The units is amperes, and here also it is amperes. And IC, what we calculated, 16 and 83.13. So the magnitude is exactly same, but the angle is 83.13 degrees. So the first part of this problem is completed, that we are able to find the currents in each branch, IA, IB and IC. Now what about IN? So if you look at this point, IA is coming towards this point through the impedance. IB is also coming towards this point through this impedance, and IC is coming like this. All the three currents are meeting here and then going back. So if I apply Kirchhoff's current law at this point, so I'll simply get IN is equal to IA plus IB plus IC. So it's a simple calculation. So let's do it right away. I'll go back to my code, and here I'll just define IN is equal to IA plus IB plus IC. And similarly, while displaying the solution, let me get the absolute value of IN and the angle of IN. So after program is executed, now I get the finally 28.03. I can round it off to 28. So this is the magnitude and this is the angle in degrees for the neutral current. So which is 28 amperes and at an angle of minus 8.2. Thus we have this system where the neutral is carrying some current. Alright, let's continue. Now I would like to find what is the complex power in this particular A phase. So the one way to find the complex power is is that if I know the current and I know the impedance. So when current and impedance are there, we can find the complex power. So what is the formula for that? So complex power in A phase is nothing, in general complex power is nothing but voltage multiplied by conjugate of current. So, but in our case, the voltage is nothing but product of current and impedance. So it is nothing but I into Z, the impedance, and multiplied by again I conjugate. So this, if I use I, Z and I conjugate, then I'll get the complex power consumed by it. So from this, I can write the formula. So if I want the A phase power, then I'll use the VAN and IA current. Similarly, here also I'll use IA, ZA and IA current. So either I can use this formula or I can use this formula. Both will work out in this particular problem. So let's try with this. So I know what is ZA, I know what is IA and IA conjugate. So from that I can find the A phase power. Similarly, what is B phase power? So B phase power is nothing but, I can write again VB and IB conjugate. So the power complex power is voltage multiplied by conjugate of current. So here if I substitute for VBN, so I get IB ZB into IB conjugate. So same way for SC, I get IC ZC into IC conjugate. So let's do that calculation and write it. I'm just going back to my earlier code. So here, let's do the calculation of powers. It's straightforward. SA equal to IA multiplied by ZA multiplied by. So the function in Octave we use is CONJ conj. So that will calculate the conjugate of IA. So this is SA. I'll just copy this. Then I'll find what is SB, what is SC. So I'm just changing this variables. So now I have all these things required. So let me just once again run the code. So here SA is there, SB and SC all are coming here. So let me write down these numbers. So 1280. So you notice that it's exactly all active power, reactive power is 0, so it is 0. So the overall unit is volt amperes because it's a complex power. So whereas individually the unit for this is watts and individually the unit for this is watts. Again, you might be aware of all that. So again, going back, 984.6. So I'll just round off to 985 and this is 1477. Minus sign is important. 985 minus of J 1477 volt amperes. Similarly, what is the SC? The SC is C phase 1024 plus 768. 1024 plus J768. So these are complex powers consumed by the load. So I'll just indicate this. So when I stress this word consumed by the load, that means when this value is positive, that means it is consumed. So 1280 watts are consumed by A phase, 985 watts are consumed by B phase, and 1024 watts are consumed by C phase. Whereas you see 0 watts are consumed by A phase. That means the A phase is not taking any reactive power. On the other hand, you notice there's a minus J1477. The meaning of that is minus J1477 watts are consumed by B phase, or in other words, 1477 watts are produced by B phase. So because this minus sign and consume, it will be 1477 watts are produced by B phase. Now, why? How can B phase produce this reactive power? If you just quickly go back and look at the circuit, so we have minus J3. That means capacitor. There is a capacitance in the B phase. That capacitance is producing an output of 1477 watts of the reactive power. And coming back to this, 768 watts are consumed because it's plus sign. That means consumed by the phase C. So actually, if you see the A phase, B phase, and C phase, you notice that there is a net reactive power generation. So if I just total all the powers, the total demand. So let's do that. The total load demand. So I can write it here S tot or ST is SA plus SB plus SC. So that is the total complex power supplied to the load or consumed by the load. It is 3288. Here you can see it, or I'll round off to 3289 and 709. So S total is 3289 minus J 709 volt ampere. So this is the total power consumed by the load. So you notice that this is watts and this is watts, and it is negative. That means the three phase load is actually net generating the watts and supplying towards the load side. All right. So another thing you notice is that, see, these are all, when I use this formula IA, ZA and IA, these are all the power consumed by each phase. These quantities are exactly same. These are also the power supplied by each phase. So there's no interference or interaction between the phases because it's a three phase four wire system. Just before we wind up this topic, I would like to draw the vector diagram to give an intuitive feel of what is happening in this circuit. So let's do the vector diagram or phasor diagram, some people might be saying. Let's begin by noting all the voltage vectors. So we have VA. So this is the VAN, which is 80 volts, and the angle is 0 degrees. So exactly horizontal line is 0 degrees. Then we have VBN, and this length is also 80 volts, and this angle is 120 degrees. So because I'm going in backwards direction, clockwise like this, so it is actually one. When I write it here, I'll write it as a minus 120 degrees. So this is considered as a positive direction, and this is considered as a negative direction. So again, you might be knowing that. Next, VCN. So VCN, again further 120 degrees, if I go back, then I'll get like this. VCN. So the value is 80 volts and this is 120 degrees. And by definition, the total circle angle will be 360 degrees. So this will also be 120 degrees. So either you can consider it as minus 240 degrees or you can consider it as plus 120 degrees. Both are same. Now let's add the currents. So for currents, let me choose a different color. Now when I refer to the phasors that we calculated, so IA is 16 amperes at 0 degrees. Now because this is amperes, I can use a different scale for amperes and different scale for volts. So let's represent it like this. So this is IA and the value is 16 and the angle is 0 degrees. This is in amperes. So because it is 0 degrees, it's just exactly, in fact, these two are on top of each other. So, but just for clarity, I have written slightly above it. Okay. Now, what about IB? When I go back here, so IB is 22.19 and angle is minus 63.7 degrees. Now, exactly I can draw it using exact measurements, but here I'll roughly draw it. So, minus 63. So, that means somewhere in the middle of this, somewhere like this, I'll get it. So, let's use a different color. This is IB. And what about the magnitude? So let's refer to the magnitude once again, 22. So slightly larger than this one. So I think I've considered that. So maybe I'll make it slightly larger. Yeah. So now this IB is the B phase current, 22 amperes, 22.1 whatever it is, 22 amperes, and at an angle of minus 63 degrees. So this angle is 63 degrees. So it is minus because this is the reference and from there I'm going back. However, what is interesting is not this angle. So this angle is what is interesting because this is the between B phase voltage and B phase current. What is the phase angle? So how much is this? So this we can anyway calculate. So from 125 subtract 63, I think I'll get about 57 degrees as the angle. So this is the phase angle between this. And also notice that the current IB is leading the voltage VB. That means looking at the phasor diagram itself, I can conclude that there is a, so this is 57 degrees. In the B phase, there is a capacitor. So I can easily find that. Now let's tackle the C phase. 16 amperes, 83 degrees. So somewhere here like this. Not exactly vertical, slightly towards the right. Yeah. So, but the length has to be same as this one. So this is 16 IC equal to 16 amperes and at an angle of 83 degrees. So this angle is 83. So obviously this angle will be 120 minus 83. So that will be the phase angle between IC and VC. So that will be 120 minus 83, about 37 degrees. So anyway, I will not mention that here. So this is about the phasor diagram. What about the neutral current, IN? So neutral current is nothing but the addition of all three. So if you actually go on adding all these three, so for example, let's take IA as it is. To IA, I'll add IB. So IB parallelly, I'll just bring it like this. So basically, this is IA plus this is IB. Then to that, I'll add IC. So something like this it will be. So something like this. So the length is again, I have to properly maintain this length and all. So this and this are should be parallel actually. So this point signifies IA plus IB plus IC. When you are adding three uh, vectors on top of each other. So from here to here will be the IN. So let's refer to that. So what is IN actually? So here you see 28 is the magnitude and 8 minus 8.2 degrees is the angle. So our rough estimate appears to be reasonable. So let me just remove all these lines. I'll use a red color for that. This is IN. So this is 28 at an angle of minus 8.2 degrees. I'll write it minus 8 degrees. So this is the neutral current. So what is the advantage of having a vector diagram like this is that just you can look at it and you see that IA and VA are in phase, so therefore there is a resistive load in A phase. IB is leading VB, therefore there is a capacitance in B phase. IC is lagging VC, so there is an inductive load in C phase. Like that we can find, and we can tell that the voltages are balanced, but the currents are unbalanced. That means the supply is balanced, whereas the load is unbalanced. So these are some of the interesting things that we can conclude by drawing this vector diagram. I hope you learned something by looking at this video. After a long gap, I have done this video. So I'll continue. We'll do the next video in which if I simply cut this neutral wire and take only three wire supply, then what happens? That is the next part of this next video that I'd like to see. So if you like my channel, please subscribe to my channel. Please press the like button. I have come back after a short break, so hopefully I'll be doing more videos regularly. Thank you.